Hello everyone, come back again to the discussion on the statistical mechanics. We are now in the microcanonical ensemble. In the last class we had seen the phase space volume corresponding to one microstate in the case of a classical ideal gas. Okay, and there we got the volume, the fundamental volume corresponding to one microstate as equal to h Planck's constant to the power 3n, as there are 3n independent harmonic terms present in the Hamiltonian, and we say the degrees of freedom is 3n there. So we have this h, the fundamental volume, omega 0 equal to h to the power 3n. Okay, 3n is the number of degrees of freedom. Now let's see the same thing in one-dimensional simple harmonic oscillator. The Hamiltonian is given by h of qp equal to half kq square plus p square by 2m. This is the kinetic energy, and this is the kinetic energy, and this is the potential energy. And we know the solution. Q is equal to a cos omega t plus phi, where a is the amplitude, omega the angular frequency, phi is the phase. So this is Q, this is the solution. This is a standard solution of simple harmonic oscillator, and P is equal to, momentum is equal to m q dot mass times the velocity. So that is q dot, if we find q dot, that will be equal to minus a omega sine omega t plus phi. Okay, q dot, we differentiate this with respect to time. So cos will change into sine, and this omega will come outside. So that will be minus a omega sine omega t plus phi. So the P is equal to minus m q dot equal to minus m omega a sine omega t plus phi, and omega is root k by m. Okay, root k by m, that is omega. And the total energy is half k a square. Okay, the standard equation, half k a square, the amplitude. K is omega is root k by m. So if we square this, we will get k equal to m omega square. So E is equal to half m omega square a square, that is a constant of motion. Why this is a constant of motion? Because the total energy is constant. We are considering microcanonical ensemble where energy is constant, or energy can vary between E minus delta by 2 to E plus delta by 2. Anyway, here the energy is constant. So the phase space trajectory of the representative point. Remember that here we are considering only one-dimensional harmonic oscillator. A single one-dimensional harmonic oscillator is there in the system. Okay, the phase space trajectory of the system, where the total energy is constant, is given by half kq square plus p square by 2m. This is the Hamiltonian, where this E is equal to constant. Okay, so basically the degrees of freedom in this case is given by 1. Why it is 1? Because we know the basic definition for the degrees of freedom is, if a given system in the Hamiltonian, the total number of independent square terms or harmonic terms present in the Hamiltonian, that is the degrees of freedom. Okay, the total number of square terms the thing is the square terms have to be independent. The total number of independent square or harmonic terms present in the Hamiltonian, that is called degrees of freedom. Here half k q square plus p square by 2m, this is the Hamiltonian, but this one has two square terms or two harmonic terms, but they are not independent because this is a constant. Taking this Hamiltonian as equal to a constant, so there is only one independent square term or harmonic term, so we say the degrees of freedom is 1. Okay, so this is a constant of m omega square q square plus p square by 2m e, that's a constant. So I am taking this e to this left hand side, so this can be written as q square by q square upon 2e by m omega square p square by 2m e equal to 1. So this is the equation of the one-dimensional harmonic oscillator. This is the equation which is derived from this. Now the thing is, this is equation for an ellipse. Okay, this is equation for an ellipse. So here P and Q, if we take a point in the phase space P and Q corresponding to this energy, so the point, that phase point will be actually moving through the phase space through an ellipse. The trajectory will be an ellipse. We know Q, P and Q cannot remain fixed in phase space. It has to change because of the Hamiltonian. The Q dot is equal to dou H dou P, and P dot is equal to minus dou H dou Q. So due to that, the P and Q will be continuously changing. So a point in the phase space that will actually move through this ellipse, because this is the equation satisfied by P and Q is an ellipse. So it will be moving through an ellipse. Now the area of an ellipse whose semi-major axis is A and semi-minor axis is B is given by, area is given by pi AB. So this is pi A is the semi-major axis is given by root 2e m omega square, and the semi-minor axis is given by root 2me. Okay, so pi root 2e by m omega square into root 2me. So as you multiply, you will get 2 pi e by omega. Okay, 2 pi e by omega, and this will be the area of this ellipse where this energy is a constant. This will be the area, that is 2 pi e by omega, and this area is proportional to the energy. Now if you restrict the oscillator energy to an interval e plus delta by 2 to e minus delta by 2. Okay, so the representative point in the phase space that will be confined to region bounded by the elliptical trajectories, okay, corresponding to e plus delta by 2 and e minus delta by 2. Okay, and we know in microcanonical ensemble we allow the fluctuation in energy in the narrow range e minus delta by 2 to e plus delta by 2. So in this case, our representative point can be anywhere in the region between, this is the trajectory corresponding to energy e minus delta by 2, okay, and this is for e plus delta by 2. So our representative point can move or it can be anywhere within this region, and it can take a trajectory, an elliptical trajectory corresponding to the energy for that, which should lie in between e minus delta by 2 and e plus delta by 2. Okay, so for the microcanonical ensemble that we are considering, the energy range e minus delta by 2 to e plus delta by 2, and this is the elliptical trajectory corresponding to e minus delta by 2, and this is for e plus delta by 2. Now the volume, or in this case area, what we are going to do is we are finding the fundamental volume omega 0, but in this case the phase space is just a two-dimensional one. Okay, phase space is two-dimensional one, the position and momentum. So since it is two-dimensional, we say it is area. Okay, instead of volume we talk in terms of area. For considering in terms of volume, there has to be at least 3 dimensions. Okay, here we have the phase space is just 2 dimensions, so we are talking in terms of area. So the area in this between E minus delta by 2 and E plus delta by 2, the trajectory corresponding to E minus delta by 2 and E plus delta by 2, this area we are calculating. Okay, this area between this, that we are calculating. So for that we have this integral, the Hamiltonian, okay, that is lying in between E minus delta by 2, E plus delta by 2. dq dp, okay, dq dp is present here, that is missing here, dq dp. So as we integrate dq dp, we have the restriction, the Hamiltonian lies in between E minus delta by 2 and E plus delta by 2. dq dp, that is present here. Okay, so what we get is this is the expression for the energy, sorry, the area of this ellipse, the area of this ellipse, that is given by 2 pi E by omega, okay, energy. So here for the area of this ellipse, that is given by 2 pi, this area of this ellipse, that is given by 2 pi of E plus delta by 2 by omega. For energy I have E plus delta by 2, and area of the entire region corresponding to this E plus delta by 2, that is given by, sorry, that is given by 2 pi E plus delta by 2 by omega, and for this it is 2 pi E minus delta by 2 by omega. So if I subtract the area corresponding to E plus delta by 2 from, sorry, the area corresponding to E minus delta by 2 from the area corresponding to E plus delta by 2, I will get this portion. Okay, so that is done here. So as we subtract, we will get 2 pi delta by omega. Okay, so we have got the area of this portion corresponding to energy E minus delta by 2 to E plus delta by 2. So that is 2 pi delta by omega. Now we are taking this harmonic oscillator problem in quantum mechanics. Here the energy eigenvalues of the harmonic oscillator in quantum mechanics are given by n plus half h cut omega, where n is 0, 1, 2. So the idea is the energy values a harmonic oscillator can take are restricted. It can take this half h cut omega for n equal to 0. It can take 3 by 2 h cut omega for n equal to 1. It can take 5 by 2 h cut omega for 2. Okay, so the energy eigenvalues of the harmonic oscillator are given by this. So in terms of phase space, in terms of if you are describing this in terms of phase space, we have the energies half h cut omega, 3 by 2 h cut omega, 5 by 2 h cut omega, like that. So in phase space, this can be represented like this. We have an elliptical trajectory corresponding to half h cut omega, where n is 0. Elliptical trajectory corresponding to 3 by 2 h cut omega energy, and another elliptical trajectory corresponding to energy 5 by 2 h cut omega. So in that way, the harmonic oscillator, if you are considering this in quantum mechanics, harmonic oscillator can have only these trajectories in the phase space. This corresponds to half h cut omega, 3 by 2 h cut omega, 5 by 2 h cut omega. So only these trajectories are possible in the phase space. Okay, so here we see this is an eigenstate. This is a trajectory corresponding to eigenstate n equal to 0. Okay, energy of h got omega, and then there are no eigenstates or possible states in between the half h got omega and 3 by h got omega, and for this eigenstate we have n equal to 1, and we have this state, and for n equal to 2 we have this 5 by 2 h got omega. So in between you don't see any eigenstate. So the first eigenstate for n equal to 0, and the second eigenstate and third eigenstate, and the difference in energy between the two eigenstates are h got omega. Okay, the difference here, it is h got omega and here it is h got omega. So what we say is, in the energy interval h got omega you have one eigenstate, because the spacing between the eigenstates is h got omega in the energy. Okay, this is half h got omega, this is 3 by h got omega. So the difference is h got omega. Here it is 5 by h got omega and 3 by h got omega. The difference is h got omega. So in each h got omega energy interval you can see one eigenstate. Okay, so there is one eigenstate in the energy interval h got omega. This is what we are telling here. So the arbitrary values of for arbitrary values of E and delta, such that delta E much greater than delta, and which is much greater than h got omega. So the number of eigenstate in the energy interval delta, that is given by delta by h got omega. Okay, the number of eigenstates within the allowed energy interval delta, because we know what we are considering is E minus delta by 2 to E plus delta by 2. So the energy difference is delta. So in the energy difference delta, how many eigenstates are there? Delta by h got omega eigenstates are there. So in the E minus delta by 2 to E plus delta by 2, the energy difference is delta, and there is one eigenstate in the energy interval h got omega. So we say the number of eigenstates within the allowed energy interval is delta by h got omega. Now within the energy interval delta, the area of the phase space is 2 pi delta by omega, that we have seen. The area of this region is 2 pi delta by omega. So we have the omega, or area in this case, which is 2 pi delta by omega, and we have the number of states in that volume or in that area, that is delta by h got omega. So if we divide this 2 pi delta by omega by this, as we did there in the case of classical ideal gas, omega was divided by gamma, so we got the fundamental volume. So here I am dividing this delta by h got omega by this 2 pi delta omega. So I am dividing this 2 pi delta by omega by this delta by h got omega, the area divided by the number of states. So if I divide the area of the phase space, in the earlier case it was volume, now it is area of the phase space equivalent to one eigenstate is now given by the area of that portion between E minus delta by 2 and E plus delta by 2, that is 2 pi delta by omega, by what? The number of microstates or number of states or number of eigenstates in that allowed energy interval, delta by h got omega. So that is equal to, as we divide this, you will get h. So the fundamental volume that we have got is h, where here the number of degrees of freedom is 1. The total number of independent harmonic terms present in the Hamiltonian is 1. We say it is 1 because the energy is fixed here, energy is constant of motion. So because of that we say the total number of independent harmonic terms present in the Hamiltonian is just 1. So the degrees of freedom here it is 1. Okay, degrees of freedom here it is 1. So we say we have got omega 0 as h. So again it satisfies our general relation. The fundamental volume is given by h to the power n, where n is the degrees of freedom. In the case of classical ideal gas, we had 3n degrees of freedom, so h to the power 3n. For the one-dimensional harmonic oscillator, the degree of freedom when the total energy is constant is 1. So we have the h to the power 1. Okay. So anyway, the general relation is satisfied. Omega 0 is h to the power capital N, where n is the degrees of freedom.